you can start. Yeah, thank you.
All right, hope everyone can hear me okay and see the slides. So welcome to our second PAWS webinar. So just as a quick reminder of the format, we'll have 20 minutes per each talk with a 5-minute Q&A for each speaker and then 10 minutes for a general discussion. I will be giving the speakers a reminder when they have about 2 minutes left just to keep us on track. And because we're trying to foster respectful dialogue, I want everyone to keep in mind these principles of discussion that help us foster a meaningful dialogue, including offering constructive feedback, sharing time, and showing appreciation, among others. So today I'm really excited to present two dynamic speakers who will be talking about CO2 and carbon cycle reconstructions. So I'll introduce both of them and then allow them to just launch into their talks one at a time. So Dr. James Ray is a reader in Earth and Environmental Sciences at the University of St. Andrews. He focuses on developing and applying the boron isotopic proxy for ocean pH and atmospheric CO2. He's an ERC grant awardee and a fellow of the Young Academy of Scotland, and he'll be presenting constraints on past CO2 change from glacial to Cenozoic timescales. And Dr. Yige Zhang is a professor at Texas A&M University. He studies past biogeochemical cycles using organic proxies, which are very close to my heart. He's also associate editor of Paleoceanography and Paleoclimatology, is a member of the advisory committee for scientific ocean drilling, and a Clark medalist from the Geochemical Society. So we'll actually start with a 20-minute talk by Dr. James Ray. So James, if you'd like to share your screen and take it away.
Great, thank you very much for the introduction, Tripti, and thank you all, well, to the organizers for inviting me and to everyone else for coming along. So the relationship between CO2 and past climate change actually has a really long history, a history of study that is about as long as our knowledge of CO2 as a greenhouse gas itself. So indeed, in the first scientific study of the heat trapping properties of CO2, which was conducted by this amazing amateur female scientist from the US in 1856, Eunice Newton-Foote, she references right up in the abstract of her paper that an atmosphere of that CO2 gas would give to our Earth a high temperature, and this, for some suppose, at one period of its history, the air had mixed with it a larger proportion than at present, an increased temperature must have necessarily resulted. These early ideas about the history of paleo CO2 and paleoclimate are also seen in Svante Arrhenius's kind of legendary 1896 paper on the influence of carbonic acid in the air, CO2, upon the temperature of the ground, where he makes the first kind of detailed calculations of climate sensitivity, if you like, of CO2's impact on global climate. And then, having gone through page after page after page of calculations that apparently he was doing in part as a side project from his, physical chemistry Nobel Prize winning work, it was a side project to kind of ease his mind through a messy divorce. He gets on to this wonderful section 5 of this paper, which, as an earth scientist makes your heart grow glad, geological consequences. And it opens, I should certainly not have undertaken these tedious calculations if an extraordinary interest had not been connected with them. And he goes on to describe that there have been ice ages, that CO2 was probably connected with those, and that CO2 would have been connected with the warmer climates of the distant past, and indeed that rising CO2 due to the Industrial Revolution had the potential to warm climate in the future. So Arrhenius made all these hypotheses well over 100 years ago, and it's been the work of a whole variety of paleoclimatologists from different fields to follow up those ideas with data. Now, one of the most iconic records, of course, of past CO2 change is this, the compilation of CO2 records from bubbles in Antarctic ice. This is our fossil record of the atmosphere from Antarctica, and it has these beautiful, well-ordered glacial interglacial CO2 cycles. And indeed, one of the big focuses of my research group is looking at these glacial interglacial CO2 cycles. But today I'm going to focus on something else. I'm going to talk about some more recent work we've been doing on high CO2 worlds. And it's of course motivated by the fact that CO2 today is 416 ppm. It's a level way above anything seen in the ice core record. And it begs the question, what does a world with more than 400 ppm CO2 look like? And to answer this question, we need to go deeper into Earth's past. So how can we do that? Well, we ran out of ice, but we have amazing records over the last 60 or even 100 million years from marine mud cores. And so we need to look to records preserved in those mud cores to help us understand past climate. And I'm going to focus today on the kind of specialty of my research group, which is the boron isotope Paleo pH meter. And without going too far at the moment into the nitty-gritty of ocean carbonate chemistry, the central point really is that CO2 is a weak acid. So when you have more CO2 in water, it follows the set of reactions that release protons, that release H+. pH, the H is a measure of these protons here. So if we can constrain pH in the past, we can put some quite close constraints on CO2. So I'm going to quickly run through the mechanisms of how this works. So boron is also a weak acid in seawater, and it has these two forms, boric acid and borate ion, and they have this acid-base dependency that's also graphed out just here. Now, there are two stable isotopes, boron 11 and boron 10, and because they are bound, boron is bound differently in these two molecules, there's an equilibrium stable isotope fractionation, whereby the heavier isotopes are concentrated preferentially into the stronger trigonal bonds. Now, if I was to sum all of the boron in seawater together, I'd get the isotopic composition of seawater, and this is constant on timescales of 5 to 10 million years. So let's now do a wee thought experiment. Let's imagine that we're in an ocean with a super low pH. At a super low pH, we push this reaction this way, and we're going to be 100% boric acid. So boric acid has to carry the isotopic composition of seawater, and there'd be an infinitesimal amount of borate ion offset below it by the isotopic fractionation factor. Vice versa, at super high pH, we'd be dominated by the borate ion. That would have the composition of seawater. There'd be an infinitesimal amount of boric acid offset above by the fractionation factor. And the really crucial point is that each of these isotopic compositions of either of these molecules is a predictable function of pH and the isotopic composition of seawater. So if we had a way of working out the composition of borate in the past, we could read along this graph and calculate pH. And the way we can do that is that the borate ion is preferentially incorporated into growing calcium carbonate. And this has been the subject of lots of work by a variety of groups to look at the kind of calibration of this proxy. I'll briefly just show one summary figure of that from work I did in my PhD. Here you can see a whole set of core top foraminifera. So what we're showing here is the pH of the water that they were growing in, their measured boron isotopic composition, and you can see that these cluster along that delta Lambda borate line, fitting our theoretical prediction for how this technique should work. So we can reconstruct pH, and with pH, we can reconstruct CO2. And I'll give one example here of the kind of proof of that concept from the recent past. This is a figure from Tom Choke, put together from data from a variety of different people. The ice core CO2 record is in black. The boron isotope-based CO2 record is in blue. And you can see it does a pretty good job of reconstructing the ice core CO2 change within 20 or so ppm. So, armed with this technique, we're going to look at how CO2 changed deeper in time. And here is the kind of starting point. This is CO2 reconstruction circa 2008. And there's some kind of absolutely pioneering early work here, which shows us that CO2 is higher in the warm climates of the early Cenozoic, and it falls into the cooler climates of the later Cenozoic. But in detail, this is slightly kind of oddly spiky in the early part of this record and oddly flat in the later part. So for the rest of the talk, I'm going to present some recent work that we've been doing to try and improve these reconstructions. Most of what I'm talking about came out in a paper last year. In fact, co-authored by Yige and some of the other people who are, I think, in the audience here today. You might also like to check out some of this work within a companion website here, which focuses on the marine methods of CO2 reconstruction, boron isotopes and forams, the thing I'm going to focus on today. But also alkanones, which you may talk about too. And then there are, of course, a broader range of other CO2 archives as well. And the great Paleo CO2 website details these proxies as well. So let's look now at the kind of updated set of boron isotope data over the Cenozoic. So I'm putting together here results from a huge kind of research effort by a variety of authors listed down here. And you can see that, over the course of the Cenozoic, just the kind of raw boron isotope data itself, it kind of it echoes the record of climate encapsulated in benthic foraminifera, which is a pretty kind of promising sign. So lower, it's plotted upside down, lower delta Lambert borate would be lower pH or higher CO2. And so you can see that there's some structure here that kind of that mirrors the benthic 018 record of climate. I'll also briefly point out that similar to the 018 record, what looks like noise at this scale is actually often resolvable orbital scale cyclicity in detail. Okay, so we want to go from delta MB to pH, and to do that, we need to know something about the isotopic composition of seawater. So I'll illustrate that with this kind of quite extreme example. Imagine I've got a measurement of boron isotopes in carbonates. If I've got modern day delta MB seawater of about 40, I'd read off the graph like this. But if that whole ocean boron isotope composition were to be changed to 30, I'd get a very different pH. Now, thankfully, the isotopic composition of seawater hasn't changed by that much, but this is still a pretty active area of research to try and narrow down the constraints on delta MB of seawater. Nonetheless, with the available constraints that we have, we can produce this fairly coherent record of pH change. And then finally, to go from pH to CO2, we need to know something else about the ocean carbonate system. This is something that you might learn in a chemical oceanography class, that the CO2 system has 6 independent components and 4 independent equations. So in other words, it has 2 degrees of freedom. We need to know 2 things about the carbonate system, so pH and something else, to determine the whole system and estimate CO2. Now, that might often sound a wee bit daunting, like, okay, you've been talking a lot about these pH records, but oh my goodness, do you not need something else that is almost as well constrained as pH? But actually here, the kind of covariances within the carbonate system help us out. And one way to illustrate that is on this plot of DIC, the total dissolved inorganic carbon, versus ocean alkalinity. These are the 2 governing variables, the master variables of the carbonate system. And I'm contouring this plot with pH in red contours and CO2 in the gray dot dash lines. And you can see that pH and CO2 are really coupled across closely coupled across this space, such that if I know pH relatively well, as indicated by this red shading, even if I put just a very broad constraint on alkalinity, as indicated by this faint grey rectangle, where those two overlap in this kind of thicker grey band, that's actually quite a well-constrained CO2 space. So although there is still some work to do on trying to improve the constraints on secondary parameters of the carbonate system, if you have a good record of pH, you can produce fairly tight constraints on CO2. And some of those different options for secondary carbonate system parameters are shown in the different colors down here. Okay, so what we left with here is our updated Cenozoic CO2 record from boron isotopes in the dark blue circles and alkanones in the lighter blue pluses, plotted alongside recent compilation of benthic 018, which is a general kind of measure of climate via temperature and ice volume. And you can see that certainly compared to some of those earlier records, here we see this much tighter coupling between climate as encapsulated with 018 and CO2 from delta 11b and alkanones. We can look at this in a variety of different ways too. So here I'm estimating surface temperature from that 018 stack using the Hansen et al. Scaling, and also plotting the measure of kind of global climate as kind of measured by changes in sea level from Miller et al. And you can see again this coupling between CO2 and climate. So let's kind of step through some of the stages of what has happened over the kind of fascinating history of CO2 and climate change encapsulated within the Cenozoic. So we'll start here at the kind of peak Eocene greenhouse, the early Eocene. I'll play these wee animations as well. This is from the amazing Climate Archive website, which has a whole brilliant set of interactive kind of model output for different paleoclimates. So this is a time where CO2 peaks at around 1500 ppm and global mean surface temperatures are maybe around 30 degrees C. This is a world that you can see from the paleogeography here, doesn't look all that different from today. India has some further progress to make northwards. We've got the remnants of the Tethys Ocean just here. But the nice thing about studying climate within the Cenozoic is we are dealing with a world that looks not too dissimilar from modern in terms of the underlying geology. But this is a world of a very pronounced difference in climate. And one of the most striking examples, I think, of that comes from the preservation of these cold-blooded creatures, alligators and crocodiles found on Arctic islands, a pretty clear sign that winter temperatures are above freezing. So as we then start to cool from peak Eocene warmth, we find our first major growth of Antarctic ice here at the Eocene-Oligocene boundary. This is associated with CO2 levels of around 800 ppm. And then our cooling continues into the Miocene. So in the Miocene, we have CO2 levels of around 500 to 600. There is an increase in CO2 in this Miocene climatic optimum associated with some meltback of Antarctic ice. And then we see the kind of regrowth and stabilization of that ice sheet as we move into a more modern world with more modern continents and flora and fauna. Finally, the Pliocene, around 3 to 4 million years ago, is perhaps our best analog for current CO2 levels. CO2 in the Pliocene is between around 300 and 450 ppm. Temperatures 2 to 3 degrees C warmer than today. And sea levels 5 to even 25 meters higher than today. Okay, so I'm going to finish out my last couple of minutes with a couple of interesting implications of this work. We do find across the Cenozoic this close coupling between CO2 and climate, and you can see that in just a basic cross plot of CO2 versus benthic 18, or if we convert that into temperature. And when plotted in a space with CO2 in log 2 units, this is showing temperature sensitivity to CO2 doublings, which are shown by these different dashed lines. You can see that across the Cenozoic as a whole, the Earth system sensitivity, and note this is not the same as equilibrium climate sensitivity because it also will include changes in slow-moving components, particularly continental ice. You can see that over the Cenozoic as a whole, the data support relatively high values of climate sensitivity, though much of this is accomplished by kind of jumps between different states, which in part is associated with changes in ice growth, or could be associated with changes in the nature of cloud feedbacks. Finally, what drives this long-term CO2 change? Well, in a very kind of simple level, the Cenozoic CO2 change reflects the balance between CO2 supply to the ocean atmosphere system, in essence adding dissolved inorganic carbon into the ocean, versus the supply of alkalinity by the weathering of silicate rocks. And the ocean takes this mix of DIC and alkalinity, and via the carbonate system sets CO2. So over the 1,000, we have about 1,000 ppm of CO2 decline over the Cenozoic, and about 2/3 of that is driven by that big kind of picture, change in the balance of DIC supply to alkalinity supply, and the remaining third is in essence a kind of in part of feedback due to changes in the equilibrium constants of the carbonate system as a function of changes in temperature and the major ion composition of the ocean. Okay, so I will wrap up there. This is work that we are continuing to do with a current ERC project. And I'll just kind of finish by noting, you know, the pretty stark message that Paleo CO2 provides for modern and future CO2 change. You know, we are already at Pliocene type CO2 levels, and Miocene or Eocene levels are possible depending on our energy choices. And we really don't want a world with Arctic alligators. Okay, thank you very much.
Okay, thank you, James, for a great talk. We have about 3 or 4 minutes for questions now, so please either unmute yourself or place your question in the chat window. I actually have a question. This might be best left for the discussion with both of you, but I was curious in the compilation that the alkanone PCO2 estimates tended to plot below the boron isotope estimates for the large part.
I think the kind of quick answer to that is actually where we have a bunch of overlapping data for the alkanones and boron. We actually, you know, there's a bunch of pretty good agreement in here. The thing that really draws the eye with the alkanones is the kind of earliest, the Oligocene in here, and actually there's really there's some overlap in the data sets around here, but there's just at present no boron isotope data in the Oligocene. We have actually just been funded along with Bridget Wade. She's leading a project to add some new boron isotope derived CO2 constraints for the Oligocene. So that is something to look out for in the next wee while. And I think also that, oh yeah, I think that's enough of an answer. Yeah. Zhang, I can see you've got your hand up as well.
Yeah, thanks for the very nice talk. Can you speak a little bit more about the Miocene and also the uncertainty range when you compare, say, with deeper time, the Eocene and the EOT? Thank you.
Sure. So, let's. It doesn't want to easily let me. Come on, I go back. Yeah. So, the Miocene, there is the Miocene, discuss. There's it's a pretty interesting time. There's a pretty striking change in Antarctic ice around this time. I mean, according to the Miller reconstruction, we get back to something that's almost close to the latest Eocene. And there's certainly a pretty striking bump in CO2 at that time. This was one of the first Paleo CO2 records that I made. The one published, it's Foster, Ray and Lear in 2012. I can remember sitting as a PhD student on the mass spec that night, watching the data come in and kind of sketching them out in my lab book on top of a graph of the O18 change, and just being so excited to see us kind of reproduce that kind of structure that you see in the O18 record there. Of course, though, that there are uncertainties in CO2 reconstruction, in all CO2 reconstructions. By the time you get to the Miocene, you do really need to start worrying about the isotopic composition of seawater. So the residence time of boron in seawater is 10 million years. And so that means for like a given, it means for the last few million years, it was essentially modern. We know it pretty well. And so so that means that for kind of the Pliocene, you can make pretty precise reconstructions. By the time you get into the Miocene, the isotopic composition of seawater has the potential to have been different, and that starts to introduce more uncertainty. And trying to nail down that uncertainty better is a big part of the work that we're currently doing. And yeah, I'll leave it at that in the interest of time.
Thank you.
Okay, so in the interest of time, we'll move on to Dr. Yige Zhang's talk.
All right, everybody can see this? Can you hear me? Okay, thank you, Tripti, and thanks to all of the organizers. Thank you for having me, and it's brave of you to have two geochemists, I guess, who are hardcore geochemists, to talk to you this morning. And I love talking to climate modelers, climate dynamicists. Very early on from my career, I realized that, we talk about climate, sometimes we geochemists have our ideas, but it's always wise to check with climate dynamicists to make sure it's not too crazy. So James laid out very nicely about the CO2. I will talk about another greenhouse gas this morning. I will focus on methane, and I will try to make it less geochemistry intense, but you probably have heard there's currently no proxy for methane, right? But people still talk about methane, especially a little while ago. There are a lot of ideas about methane hydrate release, dissociation, a huge amount of methane released into the atmosphere and causing major climate changes like PETM or even mass extinctions. But you might also notice that people talk less about it over the recent few years. So that's what I'm gonna do. I'm gonna, really think about, is this a reality or is it fiction? Okay, and share with you our recent results on this perspective. So first, let's look at the gas hydrates. We know under the seafloor, under dedicated temperature and pressure condition, methane and water combine to form these crystals, these class rates, right? So there are thousands of gigatons of methane trapped in there. So, some people think they could be the future of cleaner energy, but other folks are like, no, don't touch them. They're very dangerous, right? They're very easily subject to changes. And if they change, then they could release a lot of methane. So probably the most famous example of that is the Paleocene Eocene thermal maximum. And I guess most people are familiar with this. We see there's a rapid warming at about 56 million years ago. You guys can see my cursor, right? Okay, so that's the O18 represents the warming, and C13 representing the light carbon being released into the surficial system. And if we look at carbonate content, we see at these South Atlantic sites, carbonate percentage dropped from like 90% to almost like 0%. So we're having rapid global warming. We have light carbon in the atmosphere, in the ocean, and we have ocean acidification. So that sounds like exactly what we're doing today. And where do those carbon come from? Back in 1995, Jared Dickens and other people used the mass balance calculations to show that methane hydrate is possibly the source of the carbon. And we know methane is very isotopically light. So in that sense, we don't need a lot of methane to push the mass balance to give us the isotopic excursion. So it's a very famous idea. And after this, you're looking at a lot of like later studies. Basically, whenever we see in Earth's history, there is this rapid warming and C13 negative excursion, then the first thing I guess pop into people's mind is that, oh, it has to be methane. So methane has been used to explain the termination of the snowball Earth, like and Triassic mass extinction or mid-Cretaceous warming, you know, you name it. There are a lot of work on this front. But if we look more recent history, we look at the Quaternary, the Pleistocene, when we know things better, there is this hypothesis called the Crossword Gun. And Jim Kennett and other folks wrote a book, not just a paper, but a book on this. So they coined it the Crossword Gun because basically they see in Santa Barbara Basin sites, this is shorter time scale, this is thousands of years. So this is the last glacial, this is interglacial to glacial and Holocene. Whenever you see there is warming, these interstadial events, right? Like the ones being highlighted by these bars over here, then you see in benthicothorium, there's C13, there's an associated negative excursion. So that's their basis for this idea. They think the Crossword Gun basically fires whenever there is this warming. So if this is real, then this is a big deal, right? It clearly shows that methane played a huge role in regulating global climate. But ideas like this face a lot of challenges. You know, right after the publication of this paper, people were arguing, are these C13 signals real? Or alternatively, we know that carbonates are easily subject to diagenesis. So is this a diagenetic overprint? But a few years later, I guess this idea was hit really, really hard because this is when we were able to measure gas trapped in ice cores directly for their isotopic composition. So this is measuring methane trapped in ice core and for radiocarbons, C14, and these folks did deuterium isotope on them. And we know that during the deglaciation increase of methane, if that methane comes from hydrate, then they are going to be very negative in radiocarbon because hydrate is old carbon. They're going to be radioactively dead. So this dashed line here shows the Crossword Gun basically scenario, but this is their actual measurement. Okay, it does not match. So this is a strong evidence that the methane increase during deglaciation probably did not come from Crossword dissociation. Okay, So that's a major challenge to all of these methane hypotheses, right? The second challenge is that, over recent years, there's more better observation and modeling of methane plume coming out of the seafloor. And this is what they see. They don't make it. They don't make it to the atmosphere. They quickly dissolve in the ocean and they dissipate into the ocean. Except very, very shallow sites, they usually don't make it to the atmosphere. So they cannot directly contribute to the greenhouse effect of methane in the atmosphere. So that's the second challenge for all of these ideas. So this leads us to this question: is this real or is it just a fiction, right? So in my opinion, to answer this question, we got to figure out two things first. The one is, what are the right tools to track hydrate dissociation and methane release in Earth's history? We got to build a clear history of methane release. And the second thing is that if there was release, then how are they going to impact the global climate if they don't make it to the atmosphere? So to answer those two questions, first, let's look at how do we track methane. For those who know what I do, I'm an organic geochemist, and I'm going to argue that organic geochemistry with the biomarkers are the best way to learn about methane. But I think it's real, because if you look at the methane cycling in sediment, right? There are hydrates, there are methane hydrates, they're released in the sediment or in the water column, and very, very quickly, microbes are going to move in and they're going to oxidize methane, either aerobically with the presence of oxygen or anaerobically, using sulfate with the absence of oxygen. And they're going to produce either CO2 or bicarbonate. There are important consequences of this. I'll talk about that later. But all of that is done by microbes, right? Like anaerobic oxidation, AOM, that's done by methanotrophic archaea, the ME groups, and sulfate-reducing bacteria, SRB. And they have their diagnostic lipid biomarkers preserved in the sediment for millions of years. Crocetane here as an example. And if aerobic oxidation, that's done by bacteria, and bacteria have these hopanoids, also tend to be preserved in sedimentary records, okay? And by looking at these biomarkers, we know that whether it is aerobic or anaerobic oxidation. Aerobic, it's going to be archaea, so we have archaeal, DHEE, crocetane, PMI, a whole bunch of these biomarkers. Aerobic, bacterial origin, hopanoids, so we have diplopterol, diploptene, and their diagenetic products. So basically, we can do this. And we have this proxy, these methane proxy, based on everybody's favorite, the GDGTs. The GDGTs are the ones, everybody talks about over the last decade or so, because it's popular for the temperature proxy TEX 86. At the same time, we can actually use the GDGTs to monitor the release of methane in the sediment. So this is my master's thesis work, where we show there are methane, there's going to be methanotrophic archaea community, and they're going to make the GDGT profile look very different from normal marine. So clearly, this is when you can't apply these kind of GDGTs to look at TEX 86 and sea surface temperature, but you can calculate methane index, okay? Methane index varies between 0 to 1, and anything above like 0.3 to 0.5, then that's probably related to the presence of methane in the sediment, okay? And the good thing about methane index is that, like I said, there are thousands of reported GDGT data, and GDGT is easier to measure. So that solves the problem of, if you use other biomarkers, you might be like trying to find a needle in a haystack if you want to identify a methane release event. But people like to measure GDGT. So there are data there, and they're easy to measure new data. So that's what we're going to take advantage of. And lastly, about the proxy itself, I'll just comment very briefly. that my student Bangsu and I are working on developing this methane index more as a quantitative proxy. And we see it is related in the modern profile to methane flux and sulfate flux and the transition zone between sulfate and methane. So if it works, then potentially, we can use these measurements to reconstruct the methane flux from the geological past. So those are the tools that we're going to use. So I guess that helps answer our number one question: how do we track the history of methane? And our number two question is, does it matter if there were methane, right? And we think it does, because there are two ways that we oxidize these methane. One is anaerobic, we use sulfate, and we're going to produce bicarbonate, which increases alkalinity in the pore water and in seawater. So that's why it often facilitates precipitation of carbonates. So you often find these oxygenic carbonates at AOM sites versus more rapid release of methane. They're going to be oxidized by oxygen. And this is a picture from a deep water horizon incident back in 2010 in the Gulf of Mexico. We know it's a tragedy, but it's also an experiment for people to see that a huge amount of methane was released into the water. What's going to happen? What's going to happen after that? Okay, this is a monitoring what happened in the northern part of the Gulf. We see that dissolved oxygen was decreased. And we see, again, here you see that's the dissolved oxygen anomaly. It went down, and that's been used to consume methane, okay? So at the same time, the CO2 release is going to acidify the ocean. So this is what we think. If there's a huge amount of methane released into the water column, it's still going to matter, because potentially it could cause hypoxia and ocean acidification. And if that ocean is in equilibrium with the atmosphere, that means something for atmospheric CO2 as well. So that's the idea. So here, I'm filling in the answers. Lipid biomarkers and aerobic oxidation potentially causes hypoxia and acidification. Okay, I don't know if that makes sense to you, but now let's look at one example. Okay, I'm going to show you one example. And this is a graph that James just showed us, the famous Zachos curve that illustrates the climate change over the last 66 million. And the particular time interval I'm going to focus on is actually over here. So this is the EO transition. This is the onset of Antarctic glaciation. Very clearly, O18 dropped by 1.5 per mil. But similar magnitude, order of magnitude changes were observed during the early Miocene. But strangely enough, you see that this rebound, right? Things just pretty much went back to previous conditions. So this is a glaciation. People call it M1 glaciation, but it is a more or less a transient one, like the OI1. So what happened? And what's the role of methane during this climatic event? So that's what we're going to do. So we look at three sites from the Southern Ocean, right? There are two of them close to Tasman Sea and one closer to Antarctica, okay? And paleogeography placed them all in the Southern Ocean during the Oligocene-Miocene boundary. Now I'm going to show you the results. Okay, so two panels. The Tasman Sea sites are going to be shown over here, and the Antarctica site is going to be shown over here. And here is the O18. So you see the MI1 glaciation, you see the rebound, and here is the reconstructed sea level during this time. So during the peak of the glaciation, sea level dropped by about 50 meters or so. Okay, so what I'm going to show you first is methane index. Okay, remember that anything that is above 0.3 to 0.5, that marks the presence of methane in the sediment. All right, so now I'm going to click. There we go. So these two sites and this one site, look at that. The background value, this is pre-event more or less background value. And during the peak of the glaciation, these high values showed up. So there were methane in these sediments, okay? And also over here. So this is the occurrence in 3 sites that are separated by hundreds to thousands of kilometers. And the methane showed up at the same time across all 3 sites. So that's probably not a coincidence. And then we look further into additional evidence. We look at other biomarkers and their isotopic values. So you see the other biomarkers, they only show up when we have high methane index values, and they're below detection when it's more or less normal. And their isotopic values also confirmed that they are related to methane. Okay, so I think we have pretty strong evidence for all 3 sites to show that methane occurred during the peak of the glaciation. Why? We think the causes could be sea level because when we lose that 50 meters, we reduce hydrostatic pressure. And when we do that, we're going to destabilize the stability zone of methane hydrates. So we're going to lose this wedge right over here. We're going to lose them to methane oxidation in the pore water, anaerobic oxidation, and possibly also in the water column, aerobic oxidation. Okay, so that's the reason why we see these biomarkers occurring right over here. And we took a step further, we used the thermodynamics to look at how much methane are going to lose due to this sea level change. So we calculated the hydrate stability zone changes at different water depths, and we at different weather, climate zonation across different depths. And we used the paleo bathymetry and integrated all of them to come up with a global picture. Okay, so here's the take home. The total methane release due to this sea level drop perhaps is about 200 gigatons. That's not a huge number. I mean, if we assume 80% of that is aerobically oxidized and convert that using seawater chemistry to CO2, that's related to about 38 ppm of CO2 increase during the deglaciation phase of the MI1 event. It's not huge, but it's a significant number. It contributes to that CO2 rebound and climate rebound during the deglaciation. So I hope I convinced you that the take home is that lipid biomarkers are powerful tools to trace past methane release, and we can even work with open ocean environments where things are there's no huge amount of methane, no problem. We see them in the biomarker evidence. And ocean acidification and hypoxia due to methane aerobic oxidation could be more important than directly having them coming into the atmosphere and contributing to the radiative effect. And lastly, we saw that methane hydrates responded to, but also drive climate change, because in the MI1 glaciation case, it acted as a negative feedback. It perhaps prevented the Earth from stepping into further cooling and glaciation. Okay, I know I'm running out of time, so very, very briefly, I'm just gonna show a little primer about the PEPM, because that's the holy grail of a methane hydrate study, I guess. And we focus on the Arctic Ocean, because Arctic is gonna be, first, it's a low sulfate world, and second, Arctic is a very fresh world during the PEPM. So all of that implies that we have very limited sulfate in the seawater. If there's a limited sulfate, we might not be able to suppress methane from venting into the water column. Okay, so maybe a smaller anaerobic flux, but a higher aerobic flux in Arctic. And we do find evidence of that. So here's the gas chromatography, and here is our favorite compound. That is the compound related to aerobic methane oxidation. So we see them right here during the carbon isotopic excursion, and they are isotopically depleted. So probably we had methane released into the water column in the Arctic during the PETM, which played a role for the PETM, climatic and environmental changes. Okay, so I'm gonna stop over there, and I'd like to thank the founding agencies, thank my wonderful group of students, and Bang Su is right over there. He's our local expert on methane biomarkers. And thank you very much.
Great, thank you for a great talk. If there are any questions, please either raise your hand and unmute yourself or type them into the chat. James.
Really enjoyed that. Thanks, Yige. I was just wondering if you think that the Miocene, the Oligocene-Miocene transition was likely to have a higher kind of background amount of methane clatrate to be able to invoke than either more recent climates or perhaps a speculation on earlier climates, because what you point out via sea level becomes quite a general mechanism that we might expect to come into play for other glacial cycles, for instance.
Yeah, that's a great question, James. I put in some thoughts into that. I had the same question, like, why don't we see it over the more recent Pleistocene, when we have even larger cycles of glacial, interglacial, and sea level variation? And I think maybe the answer lies into the concept of this hydrate being like a capacitor or a reservoir that needs a recharge time. So I would argue that maybe in the earlier part of the Cenozoic, we didn't have that much of these huge sea level variations that provided longer recharge time for the system. Versus during the Pleistocene, this thing happens every 100,000 years, and maybe they don't have time to accumulate that much in that capacitor. So that's just my thought. Apparently it lacks, calculations and modeling.
Thank you.
Perhaps we can open up the Q&A for a general discussion as well. So, oh yeah, Jack, go for it.
Oh, yep, sorry, I couldn't unmute myself. Perhaps intended. So this is mostly for James, I guess, but maybe for both. But so James, you showed that like the early Cenozoic has really large variability in reconstructed CO2, and that there is some like orbital scale cyclicity. And so I guess can you suggest some hypothesized mechanisms where you can get orbital scale cyclicity that in the absence of continental glaciation, and perhaps also at the scale that you see, it's like swinging between 400 and 2000 ppm. It's pretty huge.
Great. Okay, thank you for the question, Jack. Let me just see if I can quickly share my slides again. I think the kind of quick thing that I'd mention is that the specific slide that I showed on variability with those kind of 400 numbers. Let's see. Hopefully you can. There we go. Can you see my PowerPoint?
Yep.
This is the Pliocene with these kind of 300 to 400 ppm glacial. That's a kind of, so that's a bit like a continuation of Pleistocene glacial cycles. But what about the earlier Cenozoic? Well, to date, we don't really have orbital resolution in those records. We do have some variability. The biggest kind of spikes that you can see in variability are the PETM and the KPG impact. So both times where there's quite a lot of big picture stuff going on. So some a bunch of quite viable mechanisms for big changes in ocean carbonate chemistry. But something we are now working on is producing more orbitally resolved records in this window. And it will be really interesting to see as we do that, does some of the variability within the data, does that kind of resolve into orbital cyclicity? And indeed, I think you're kind of touching on a really, really fascinating point, which is that there are pretty big changes in climate in the Eocene on an orbital scale, and yet CO2, the kind of baseline, is higher, and so to get changes from that higher state, you need more CO2, given that it scales with doublings. So that kind of raises some quite interesting pictures about carbon sources on the one hand, though on the other hand is slightly kind of counterbalanced by the concept that actually in the Eocene you have a higher climate sensitivity world. So yes, I hope that gives a kind of a bit of a flavor of an answer, and watch this space for more of that orbitally resolved data.
Yeah.
Okay, so I have a related question, because here you say that, say, for the Eocene climate optimum, we have a lot of variability in the CO2 reconstruction. My question is from climate modeling perspective. If we want to use the CO2 in our model simulations, right now I think we are using a bulk average. Do you think that's a good practice, considering that the radiative forcing from the CO2 is not linear? Thank you.
I guess it seems that it seems like a very good place to start, right? And for a couple of reasons, the primary one being that both our CO2 records and indeed most of our temperature records, most of when we think about kind of the things we might actually try and use for GMST, aren't yet really kind of detailedly orbitally resolved. That is increasingly coming, but I don't think we're quite there yet with the all of the aspects of data to look with the kind of work that you've done recently, for instance, at the orbital scale variability. I think though that is coming, and it's going to be fascinating, both from a data point of view and then from a modeling point of view. And I just kind of highlight that the analogy with the work done in this paper by Miguel Martinez Botti in the Pliocene, my slides are jumping, is a good one, in that there's a lot of value to exploring, say, sensitivity from short timescale variations in a kind of shorter time window, because a bunch of your uncertainties, both in terms of modeling and in terms of data, a bunch of your uncertainties somewhat collapse. So for instance, from the data side, on these kinds of short timescales, we end up being able to constrain CO2 change quite well, because, for instance, we know that Delta Lambia seawater had to have been constant. And it turns out that even if we don't know its absolute value very well, the knowledge that on a timescale of a few 100,000 years, it's constant, allows us to shrink the uncertainties. And then from a modeling point of view, you you start to be somewhat limited in what you can do in terms of changes in land surface. So I think it's a cool place to get to, and I hope that, I think it's the direction a lot of the community is heading towards.
Thank you.
If I can jump in, unless there are any other questions. This is more a question for Yige. If I understand it right, you're planning on going back through the data we have for GDGT distributions to calculate methane index. Can you speak a little bit about that work and sort of the challenges posed by maybe different standards of data archiving?
Yeah, Tripti. So, well, I guess thanks to a lot of other efforts like temperature compilation and a general tendency that people are sharing more of their data. Before, I remember back in the days, when we first started to measure GDGTs, like you can't find the raw like GDGT composition data over there, so you can't calculate for methane index. But now most of them, I would say, is available. So we are actually able to screen the data, and we saw some interesting trends over the Mesozoic and Cenozoic when GDGTs are available, and they might be tied to some like general, the climate and environmental scheme of the Mesozoic and Cenozoic. But that's a preliminary work. Well, we are not fully understanding, but we do see some interesting patterns over that long term. When do methane occur, and whether they're correlated with factors such as sulfate concentration or that kind of things. We do see that.
Okay, we're already a few minutes after the hour. So let's thank the speakers again. Really great talk. Thank you very much. And thank everyone for joining.
Thank you.
So see you in a few weeks.
So good to have James here, so I don't have to answer all of the hard CO2 questions.
And really nice to see you too, Yige, in case anyone had asked me about the alkanose component. Yeah, thanks for having us. It's really fun to talk about this. This was like...
Did you say that Miocene is disgusting? Or
no, I certainly didn't. It's wonderful. Oh my goodness, I hope nobody else heard me say apparently the Miocene is disgusting.
That's not what I heard.
Okay.
Yeah, bro. Anyway, yeah, nice to see you again, and nice to actually kind of talk about this. This was something that in normal times I'd have talked about while kind of developing a lot of this, and actually it was like a lot of time spent in our spare bedroom in lockdown, sweating over pulling together these data sets. So this is actually the first time I actually talked about it out loud. I hope it wasn't too intensely geochemical.
No, I think it's really cool that we can maybe start to get a picture of the role trace gases have played in temperature in the past, by resolving both CO2 and methane potentially. So it's exciting work.
Yeah, except that we still don't have a proxy for methane, right?
But methane release, that was cool to see. Anyway, I've got to run for a bus. Nice to see you guys. Hope to see you soon, maybe this summer.
Thank you, guys.
Thank you. Bye.
Bye.
Bye-bye.